Okay, in last lecture we have seen IIR designed by bilinear transformation. In this lecture we will discuss the infinite impulse response filters specifications. In this particular lecture we will discuss these specifications and design approach. The first part is design procedure for an IR filter starts with a normalized analog low pass filter, also called prototype filter. Then prototype filter is transformed into the desired frequency selective digital filter in second step. Then we will study different families of analog filters such as Butterworth and Chebyshev of analog low pass filters. These filters are typically used as prototype filter. Before discussing families of filters, we will first discuss analog filter specifications. Analog filters are traditionally specified using quantities as E and A, where E is passband ripple and A is stopband attenuation. Next point is, in generally, the design of IR filter is usually done by converting analog filters into equivalent digital filters. So we will first see the response characteristics of IR filter, and then through this response characteristics we will try to find out the response characteristics of analog filters. The response characteristics of IR filter will look like this. This is the relative specifications of IR filter. We will have a maximum gain of 1, and with the attenuation in passband, that will be 1 upon under root 1 plus epsilon square and 1 by A in stopband. Now comparing these specifications with FIR filter specifications, we get 1 by under root 1 plus E square is equal to 1 minus delta P over 1 plus delta P, which is equal to delta 1. Similarly, for stopband, 1 by A will be equal to delta S over 1 plus delta P equals to delta 2. Then we can find out the value of E and A with respect to delta 1 and delta 2. Then E will be equal to 2 under root delta P over 1 minus delta P, which is equal to under root of 1 by delta 1 square minus 1. Similarly, we can find out the value of A, which is equal to 1 plus delta P by delta S, or equal to 1 by delta 2. Now we have find out the relationship between E and A, where E is related to passband ripple, A is related to stopband attenuation, with the delta P and delta S of FIR filter. Now we also want to find out the relationship between attenuation in passband of FIR filter with E and attenuation in stopband for FIR filter with A. We know AP is the FIR passband attenuation is equal to minus 20 log base 10 1 minus delta P by 1 plus delta P. Then we can write it as minus 20 log base 10 1 over under root 1 plus E square, which is related to passband ripple of IIR filter. AB will be equal to 10 log base 10 1 plus E square. Similarly, for stopband attenuation, AS in FIR filter will be equal to minus 20 log base 10 delta S over 1 plus delta P. Substituting the value will give minus 20 log base 10 1 by A will be equal to, so it will be plus 20 log base 10 A. So we have find out the relationship between passband attenuation of FIR, passband attenuation in IIR. Similarly, AS is stopband attenuation in FIR. This is stop band attenuation in IIR. Then we can find out the value of E and A in terms of AP and AS are E equals to 10 to the power AP by 10 minus 1 and A will be equal to 10 to the power AS by 20. Now linking digital filter with analog filter will lead digital omega P will be equal to omega P over Fs is equal to 2 pi Fs over Fs, and omega s will be equal to omega s over Fs, which can be written in 2 pi F by Fs, where this F is stop band frequency. Now this Fs is nothing but 1 by T, that is sampling frequency. Now we can find the magnitude specification. In analog domain as magnitude square. We generally represent magnitude specification in analog domain by magnitude square. So the relation will look like as 1 by 1 plus E square to 1 is pass band, and it will be 1 by A square for stop band. So then we can draw the magnitude square response for analog filter as 1 by 1 plus E square from 0 omega P. From omega s onwards it will be 1 by A square. This is the analog filter response. Analog filter is usually designed with magnitude response alone, as it is convenient with magnitude squared response to design an analog filter. Now we have represented our analog response in magnitude squared part. Then it is important to find out the relation between squared magnitude response. So we can write H omega equals to HAS for S is equal to J omega. In some books there is a J written in this particular part. In some books it is not written. So we are not generally writing it as J omega. We are just writing HA omega. As the coefficient of HAS are real, then we can write HA omega square will be equal to HA omega multiplied with HA conjugate omega. Now if we write in terms of J, then it is pretty easy to understand that this is HA J omega and this is HA minus J omega. Then we can write this as HAS and this as HA minus S for S is equal to J omega, as we know. Then we can write HAS multiplied with HA minus S will be equal to mod of HA omega square, where omega is S by J. Now observing from this equation, we can say poles and zeros of the magnitude squared function are distributed in the mirror image symmetry with respect to the J omega axis. Next observation is to maintain the real coefficients of the filter, the poles and zeros should occur in a complex conjugate pairs. And then if HAS has to be causal and stable filter, then all its poles should lie in the left hand plane of the S plane, which is the necessary condition for the stability, as we have seen previously. Then the next point is, as all the poles are lying in the left hand plane of the S plane, then we can assign all the poles of HAS and HA-S to HAS. After poles, there comes zeros. For zeros, they can lie anywhere in the plane. So there is no restriction for zeros, but there is a restriction for poles. Then, as zeros can lie anywhere, but we will choose only those zeros which will lie either in left hand plane or at the j omega axis of this function HAS with HA-S in S plane. The filter which will satisfy all the previous conditions which we have discussed will be called minimum phase filter. That's all for this particular lecture. In next lecture, we will discuss analog Butterworth filter for the implementation of IIR filters. Thank you.